So, yeah, jeez, Katie. All right, so chapter 6, we are going to start talking about how we can make inferences for data. So far, chapter 5, all we talked about was, I can find probabilities and talk about how likely something is to happen. But now we want to start being able to actually make inferences for the population based on information. So the first thing we're going to start with is something called a confidence interval. So if you want to estimate some value of the parameter from a population, you can take a sample, calculate the statistic from that sample, and then the statistic, that doesn't sound like the right word. So the sample statistic is an estimate of the population parameter. But as we discussed in chapter 5, as you do different samples, you get different sample statistics, which then gives you a different estimate for the population parameter. So instead of just giving one estimate of the population parameter, what a confidence interval does is it gives an interval of plausible values based on the sample data you do have. So confidence interval, if you remember interval notation, it's kind of like that. It's just going to be parentheses and numbers. So if you kind of think back to when we were talking about this in chapter 5, we talked about the pink card thing. So in this case, all we know is that you have 100 cards, and each person is going to pull out 10 cards and record the proportion of pink. And then in this case, we don't know what the actual proportion of pink cards is, which is going to be more similar to real life than what we were doing in chapter 5. So we want to know, is what we got exactly equal to our population parameter? And then we assume that our population parameter is somewhere around p hat, but how close to it is it likely to be? So a couple things we need to review from chapter 1 before we do confidence intervals. So we're going to revisit the 68, 95, 99.7 rule. So just to kind of review the conditions for a parameter first. So remember, your center is your mean. So the mean of p hat is equal to p as long as you have either random assignment or random sampling. The shape is normal, and that's where you check the NP greater than or equal to 10 and the n times 1 minus p greater than or equal to 10. And then the spread, which is our standard deviation formula, is the square root of p times 1 minus p all over n. And that formula is going to slightly change for confidence intervals, but not to the extent where it's a different formula that we just don't use p anymore. We'll use p hat. And then that one is our 10% condition. So your sample size has to be less than or equal to 10% of your population. So the conditions don't change for a confidence interval. They're the exact same conditions they were when we had just regular sampling distributions. So 68, 95, 99.7 rule. So 68% of data is one standard deviation from the mean. 95% of the data is 2 standard deviations from the mean. I know, right? And then 99.7% of the data is 3 standard deviations from the mean. So just kind of reviewing that from chapter 1, because that was a really long time ago. It was a really long time ago. So, as I kind of already said, a confidence interval is an interval of plausible values for your unknown population parameter. And the way we construct a confidence interval is we use a chosen degree of confidence so that our parameter will be captured inside that interval. And there's no way for us to know for sure that the population parameter is actually in that interval, but we'll talk about how choosing your level of confidence affects it. So the chosen degree of confidence is called the confidence level. I've said it a couple times, but confidence level. Which gives us how much information about how much confidence we have in the method used to construct the interval. So a confidence level gives it's called the long-term capture rate used to construct the interval. I don't really need to know that so much. And then depending on what percent confidence, because the confidence level is a percentage, so right now we're going to call it C% because we're going to generalize it. So whatever percent confidence you want, it will give your interval of plausible values. For your parameter. So the most basic definition, just in general, of what a confidence interval is it takes your point estimate, which is going to be our mean in this case, and it adds and subtracts a margin of error. So like the margin of error, we'll talk about how that's calculated in a little bit, but the margin of error is like going to give you the interval because you'll add and subtract it from whatever your estimate is. So the most common thing that people struggle with is they think that a confidence level tells you what percent confident you are that your population parameter is actually in the interval. And that's not what a confidence level gives us. A confidence level tells you that if you were to repeat your confidence interval many times, you'll be that percent confident that percent of intervals will contain the true population parameter. So if I want to be 90% confident, like if I have a 90% confidence level, if I constructed a bunch of different intervals based on different like p-hats, 90% of the confidence intervals constructed would contain the population parameter. So it's not that I'm 90% confident that my interval contains the population proportion, it's that 90% of intervals created contain the population parameter. It's a very hard thing for people to wrap their minds around because they think that it should be what percent confident you are that the interval you've created has the population parameter, which is not what it does. So when we are interpreting a confidence interval or a confidence level, when we are going to write sentences for our confidence intervals, and they're going to be very, very similar sentences, they're all going to start the same way. Then you'll like input your values and then your context. So they're all going to start with we are and then whatever percent confident that the interval and then whatever your interval is captures and then whatever your parameter is in context. So very similarly to sampling distributions where we had the basic same sentence, we just changed out for our situation. That's the same way we interpret confidence intervals. And then this is just kind of an example of the confidence level interpretation. So if you take many samples of the same size from this population, 95% of them will result in an interval that captures the actual parameter value. So you'll definitely have to be able to interpret a confidence interval every time. The confidence level, I'll usually only have you interpret usually on a quiz. just to make sure you understand what it is. Usually on an assignment, not so much. I focus mainly on the assignments of can you construct and interpret the interval, but you will have to know how to interpret the level as well. So let's talk about how the interval is constructed. So we need something called a critical value. So the critical value is calculated based on your level of confidence. And it's the value that makes the interval wide enough to have whatever level of confidence you have. So the critical value is basically your number of standard deviations. Yes?
Were we supposed to write something under confidence intervals?
Nope.
Oh.
This is very generic, like this is what it looks like. So the critical value is basically your number of standard deviations to have your percent of area in between. So our statistic, which is our sample, and then plus or minus, and then the critical value times your standard deviation, that's what gives you your margin of error, which I'm going to abbreviate ME because I don't like to write out margin of error. So the margin of error is calculated by taking your critical value and multiplying it by the standard deviation. So there's two things we're going to look at. We're going to look at how the confidence level or the critical value affects the width of our interval. We'll also look about how sample size affects the width. So we'll start with confidence level. So confidence level affects your critical value. So if you are going to increase your confidence level, it increases the critical value, which would then do what to the margin of error? Make it bigger or smaller? If you keep increasing your critical value. You have a 50-50 shot. It makes it bigger. So if you increase your confidence level, you increase your margin of error, which means you have a wider confidence interval. Which makes sense if you think about it, because if you want to make sure your whatever percent of intervals contain your population parameter, you want to have a fairly large confidence, which would mean you have a very large critical value because you're making sure that it's wide enough. So on the other side of things, what do you think happens if you decrease the confidence level? How does it affect your margin of error?
Smaller.
It makes it smaller. So you decrease your confidence level. You decrease your margin of error, which makes you have a narrower, I hate that word, confidence interval. Narrower is a word. I just don't like saying it.
Is that for confidence interval?
Yeah, for confidence interval. I do a lot of abbreviating. More narrow. Smaller also works. Thinner. I don't like thinner when it comes to confidence interval, though. It's weird. Yeah, you're thinly confident. All right, so now we're going to talk about how sample size can affect your confidence interval. So going back to the same formula, I'm not going to relabel what the margin of error is. Margin of error is still the same thing. So standard deviation is solely affected by your sample size. So what would happen to standard deviation as you increase sample size? It decreases. So standard deviation would decrease, which means what happens to the margin of error? It decreases. So if you increase n, you decrease standard deviation, which decreases margin of error, which actually gives you a narrower confidence interval. So opposite effect. So on the reverse side of things, what happens if you decrease the sample size? Yep. Increases your standard deviation, which increases your margin of error, which would give you a wider confidence interval. So when it comes to constructing confidence intervals, you want to have a small margin of error, just in general. Like, you know that from science usually, is that you don't want to have a large margin of error. You want to be pretty small margin of error. So there's two ways you can get a small margin of error. You can either have a large sample size, because as we saw, large sample size, lower margin of error, or you can have a smaller confidence level. Now, do we want a small confidence level? No. So typically, to help keep our margin of error small, we take larger sample sizes, because we don't want to have a small confidence level. We want our confidence to be pretty high. So to kind of offset the fact that our confidence level is high, we take large sample sizes. Yeah, very large section. We're not going to get through it all today.
I was gonna say, like,
There's a lot going on. We're not getting through it all today. So when it comes to constructing a confidence interval, we do assume that our data is going to come from an SRS, which we will check conditions, so we'll know it's going to be random. And then the margin of error only covers chance variations. I don't know why I put an S at the end. Due to random sampling. So the margin of error has to do with your chance variation, because that's where your sample size is, like, increasing or decreasing. That's how you get your spread. So that's due to random sampling. Before we actually talk about how to calculate a confidence interval, we're going to talk about interpreting them. So we have that a New York Times / CBS News poll asked a random sample of U.S. adults the question, do you favor an amendment to the Constitution that would permit organized prayer in public schools? Based on this poll, the 95% confidence interval for the population proportion who favors such an amendment is 0.63 to 0.69. So we're going to interpret this. We're going to figure out our mean and standard deviation, mean and margin of error, and then we're going to answer a question about that. So let's start with the interpretation. So when we are writing a sentence, it always starts with we are, and then you plug in your percent, so 95% confident that the interval not the interval, that between, I don't know why I put the interval, that between 0.63 and 0.69 of U.S. adults favor organized prayer in school. So it takes the percent confident, then your interval, and then whatever your interval is talking about. You could also technically say we are 95% confident that the proportion of U.S. adults who favor organized prayer in school is between 0.63 and 0.69. You can switch the order. I don't care. It means the exact same thing. So whether or not you put the interval before the wording or after, doesn't matter, because it puts the same point across. All right. So for the second part, finding your point estimate, which is the exact same thing as your mean, and then your margin of error. So in a confidence interval, the mean is directly in the middle. So how do you find the number that's in the middle of 0.69 and 0.63? Add and divide by 2, which I'm pretty sure is going to give us 0.66. The margin of error is then the distance from that mean to either value in your interval, which will be the same. So what's the distance from 0.66 to 0.69 and 0.63? 0.03. No, the margin of error is just 0.03. Other way you could have done it because the margin of error is then like the distance, you could do 0.69 minus 0.63 divided by 2. And that gives you the margin of error because it's the distance between the two divided by 2. So, couple options. We don't have enough information at this point to then so we know the margin of error, that is our critical value times our standard deviation. There is not nearly enough information in this problem for us to actually figure out our critical value and our margin of error. Sorry, critical value and standard deviation. We just know that that's what happens when you multiply them together. All right, last one. So based on the poll, a reporter claims that more than 2/3 of U.S. adults favor such an amendment. Use the confidence interval to evaluate this claim. So what we're basically saying, is the reporter correct or incorrect? So when you go back to our confidence interval, which is 0.63 to 0.69, 2/3 is what decimal?
0.66.
Yes. Does our confidence interval only contain values that are more than 2/3? No. So the reporter is incorrect. Because based on the confidence interval, the proportion could be smaller. Now, if our interval was 0.66 repeating or 0.67 to 0.75, then we're good. The reporter is not wrong because every value in our interval is greater than 2/3. But considering we have values that are not greater than 2/3 in our interval, we can't make the claim that more than 2/3 of U.S. adults. It could be more than 2/3. Part of our interval is more than 2/3, but not all of it. Yes?
How did you find the margin of error?
So the margin of error is the distance from your mean to your values in your interval. So 0.66 to 0.69 is 0.03, and the same thing in the other direction. Yes?
Can you just explain what you just said for Steve? I'm so lost.
Okay, so the reporter claimed that more than 2/3 of adults favor the amendment. So 2/3 is 0.67. So he's saying more than 0.67 of adults favor the amendment. If we look at our confidence interval says that the true proportion who favor it is somewhere in between 0.63 and 0.69. So our interval does not contain values that are only more than 2/3. So his claim is incorrect because our interval says it could be smaller than that. It could also be larger, he could be correct, but our interval does not support his claim. If our interval had been 0.67 or even 0.68 to 0.7 something, then we could say he's correct because our interval only contains values that are greater than 2/3. It works the same way if he had said less than 2/3 of adults because, again, not all of our values are less than.
So in order to support a claim, the values in that interval have to be...
They have to support the claim.
Yep. So if it's greater than, they have to all be greater than. If it's less than, they have to all be less than.
Yes. Yep. Here. Multiple choice example. All right, so researcher plans to use a random sample of families to estimate the mean monthly family income for a large population, and they are deciding between a 95% and a 99% confidence interval. So we want to look at the difference between a 95 and a 99% confidence interval. So it kind of goes back to what we talked about before. If you increase your confidence, you increase the width of your interval. Okay. So that's the most basic thing that you need to know. If you increase confidence, you increase the width. So that helps us to get rid of A and C, because those both say they would be narrower, and we know if we're increasing confidence, it's going to be wider. Okay. If you increase width, it does change the risk of you being incorrect. So it's not E, it's not the same, because obviously it's going to either be more or less accurate. So if we have a wider interval, we are more likely to be correct, because it is more likely that the intervals that we construct contain the population parameter. So it's going to be wider and would be a smaller risk of being incorrect. The way that it's worded, it's based on your risk of being incorrect. So smaller risk of being incorrect because you're going to have a wider interval. Wider intervals are more accurate than narrower intervals. What's the next page? Is it the conditions? Yeah. We'll do the conditions and probably talk a little bit about how the standard deviation formula changes, and I'll stop there. And won't talk about the critical values yet because I don't think I have enough time to talk about them all. So that'll probably be where you guys start the notes tomorrow. We'll see. I got 6 minutes. All right, so conditions do not change from when we were looking at sampling distributions. So you still have to check that it is random. So either you have an SRS if you're sampling, or random assignment if you're doing an experiment. It still has to be independent. And your 10% condition n less than or equal to 0.1 of your population. Now remember, if you're doing an experiment, independence is assumed because each trial is independent of any previous outcomes. So you don't need to check the 10% condition for an experiment because that's the only time we can assume independence. If it states in the problem you can assume they're independent, also you don't have to check the 10% condition. And then lastly, normal. So you have to check your large counts condition, which is NP greater than or equal to 10, and N times 1 minus P greater than or equal to 10. Oh, wait, this is where it changes. So now we're using P hat. This is where it changes from a sampling distribution because we won't actually know the population parameter. We're creating a confidence interval that can contain it, so the only information we're given here is a P hat. So now we use P hat. This is where it's going to start to get confusing because sometimes when we check our conditions, we're going to be using P hat. Sometimes we're going to be using P, and it's whether or not you're doing a confidence interval, or we'll talk about next week, we'll talk about significance testing. They have a population parameter. So the only time you will use P hat in any of your conditions is with a confidence interval. That is the only time you will use P hat in your conditions. So that then changes our standard deviation formula. Because when we did standard deviation for a sampling distribution, we had P, so we used that to find our population proportion, which we no longer have because now we have a sample only. So our standard deviation formula is now the square root of P hat times 1 minus P hat all over N. So P hat is used. Oh. It also is going to change the name of what we call standard deviation. It is now called standard error. I really am going to keep calling it standard deviation, but technically it is now called standard error because it's based on sample data and not population data, and standard deviation is technically used if you have population data. You can still call it standard deviation. It's going to be fine. I'm not going to count it as wrong. We're still going to use the same symbol. It might be called standard error in the wording of things, but just know it still means standard deviation. All right. I don't want to talk about the critical value because I don't have enough time to go over how we calculate it. So tomorrow you guys I'll find out what part of the video starts with critical value, and sure. And that's where you'll start. You'll finish the notes for tomorrow, and then your hybrid assignment is going to be a 6.1 practice. It'll be a book widgets. It'll be posted on Canvas, so nothing on paper. for hybrid.